Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 12, Organic Chemistry 3. Carbohydrates and nucleic acids. Oxidation of monosaccharides. Oxidation to aldonic acid. Treatment of aldose with bromine water oxidizes the aldehyde to carboxylic acid. The aldehyde functionality of the aldose will transfer to carboxylic acid by treatment with bromine water. So glucose will turn out to be gluconic acid. Aldonic acid, so glucose will be gluconic acid. The mechanism is through the formation of hydrates first, then deprotonation to form the anion. Bromine will react with it to form HBr2-, which dissociate to H+ and 2Br-. To know more about the mechanism, you can go and read Australian Journal of Chemistry, volume 17, page 1210 in 1964. Like acid gamma and delta hydroxy acids, gluconic acids exist in acidic solution as lactones called aldonolactones. The lactones with 5-member rings are somewhat more stable than those of 6-member ring. Let's try to do the 6-member ring lactone structure from gluconic acid. Well, this is the first step, is taking from Fischer projection to the 3D. Then rotate this 90 degrees. Now we have the OHs. Here this OH needs to be in the back, close to the COOH, so we have to rotate around this carbon, the 3 group together, so we get this structure now, the OH in the back and COOH in the back, close to each other for the lactone formation. Well, it gives 6-member ring, OH down, OH down, OH up, OH up, OH down, OH down, CH2OH up, CH2OH up. This is the delta gluconolactone structure. For the gamma lactone, alpha, beta, gamma, so we would like to get the OH here in the back, so we have to rotate to get the OH in the back. Now it's close to the COOH, lactonization to give the D-gamma gluconolactone of this structure. Well, reacting sugars which have free aldehydic functionality with mild oxidizing agents like Fehling's, Benedict's, and Tollens reagents will lead to the formation of the carboxylate ion in a solution. So the aldehyde will be oxidized to carboxylate. Well, what will happen for Fehling solution, which contains copper 2 ions complexed with tetraacetate ion in sodium hydroxide? Or with Benedict's, which is the same, but instead of using tetraacetate to complex with copper 2, we use citrate ions. Well, In both cases, we will get a red precipitate of copper 1 oxide. For example, here we have glucose, which exists in cyclic and open structure. Open structure has free CHO, will be oxidized to carboxylate, and the Fehling copper 2 will be reduced to copper 1 oxide as brick red precipitate. Here is the oxidation reduction reaction, where the aldehyde will be carboxylate and copper 2 will be copper 1. And here is the complete equation for this oxidation reduction reaction. Once again, the aldoses which exist in the cyclic hemiacetal and open chain tautomerism has the aldehydic functionality here, which could oxidize with ammoniacal silver nitrate in presence of base, we call it Tollens reagent, to form the carboxylate and deposit silver metal. Once again, the oxidation reduction reaction, aldehyde with 3 equivalent base forming the carboxylate, ejecting 2 electrons with 2 silver 1 will lead to the formation of silver metal plus ammonia, and the sum of the equation will be aldehyde with silver 1 complex with 3 equivalent base to give the carboxylate, silver metal as a mirror, water and ammonia. Of course, the alpha hydroxyketone also are able to give positive Fehling and Tollens. Why? Because we mentioned before that the alpha hydroxyketones have the capability and the ability to tautomerize to aldehyde in presence of base. So under the reaction condition, the alpha hydroxyketones will transfer to aldehyde, and then the aldehyde will be oxidized to carboxylate, reducing the Tollens reagent to form silver mirror. As we mentioned, Tollens reagent must react with open chain form which has a free aldehyde. If the cyclic form cannot open to free carbonyl compound, the sugar does not react with Tollens reagent. Hemiacetals are easily opened, but an acetal is stable. So if we have here, this is the anomeric carbon, OR, OR, so this is acetal, cannot open to aldehydic analog, so this is non-reducing sugar or not reducing sugar. It will not reduce the Tollens reagent and we have no reaction. Well, which of the following are reducing sugar? Methyl D-galactopyranoside of that structure. Again, this is anomeric. This is acetal, cannot open. This is stable, so no open structure, no aldehyde functionality. This is non-reducing sugar, will not reduce Tollens. Beta L-iodopyranose, it's an aldose. This is the anomeric. This is hemiacetal, can open to L-idose open chain with free aldehydic functionality. This could easily be oxidized to carboxylate, reducing Tollens to silver mirror. Oxidation to aldaric acid can be done using dilute nitric acid. Here, carbon number 1, the aldehyde functionality will be carboxylic group, and the terminal CH2OH, the primary alcohol, will transfer again to COOH, and the product will be aldaric acid, older term glycaric or Saccharic acid. So if we start here with glucose, CHO and CH2OH, COOH, COOH will be glycaric acid. Glycaric acid. Like aldonic acid, aldaric acid in acidic solution form lactones. Two different 5 members lactone are possible. So we have here the possibility of 6,3-lactone. Another possibility will be 1,4-lactone, and bis or dilactone 1,4,6,6-dilactone. So having glycaric acid structure, Fischer projection, see here carbon number 2 is R configuration, and on carbon 5 it's S configuration. This is a systematic name. Now, seeing it in 3 dimension will be like that. Here is carbon number 1, here is carbon number 6. Now, all what we have to do is rotate the 3D 90 degree clockwise. We get this structure. We would like to get the OH on carbon number 4 in the back, so we have to rotate the 3 groups HOH and CHOH, COH, right? When we rotate that, we get the OH in the back. Now it's close to the COOH for lactonization. That will give you this D-glucaro 1,4-lactone. Remember, we did not touch the configuration, the asymmetric center on here, on carbon 5, which is S configuration. So the structure on carbon 5 we did not change and retain S. To read more, go to European Journal of Organic Chemistry 2017, page 6811. You will find more information on the formation of this lactone. Now, if we have the glycaric acid, but we rotate this 90 degree anti-clockwise, then we get again this structure. We would like the OH to be closing the back to the COH. Well, we rotate, we get this in the back. Now what we get out of the lactonization is, again, we did not touch carbon number 2, which is R configuration. So the product will be R configuration in here. The OH here is up, the OH here is up, so it's up, up. That's D-glucaro 6,3-lactone structure. Two sugars, A and B, are known to be glucose and galactose. but it is not certain which one is which. On treatment with nitric acid, A gives optically inactive aldaric acid, while B gives optically active aldaric acid. Which sugar is glucose and which is galactose? Well, from the glucose structure, the OH at carbon 5, right? Here 4 right, 3 left, 2 right. This is the glucose structure. Oxidizing it with nitric acid will give glycaric acid. This compound has no symmetry, so it is optically active. Accordingly, glucose should be B. On the other hand, the galactose here is right, left, left, and right, OHs. Oxidizing it with nitric, then we get COOH, COH. This molecule has plane of symmetry here, so it is mesostructure and optically inactive. So that's definitely glycaric acid, and A should be galactose. Oxidative cleavage of sugar. The reagent that leads to C-C bond rupture is periodic acid HiO4. This compound oxidatively degrades vicinal diols to give carbonyl compounds. So we have here diol, 1,2 diol, with periodic acid forming cyclic pair iodate ester 5-member ring, which opens to 2 carbonyl compounds and HiO3. Each COH needs one equivalent HiO4. Well, if I have glucose, then we need 5 HiO4. C1 is aldehyde, will be oxidized to formic acid. Each one of these OH will get around it 2 HiO4, so it will transfer again to acid, while the primary terminal CH2OH will be formaldehyde. So, breaking C-C bond in the sugar consume 1 HiO4. Each aldehyde and secondary alcohol will give formic acid. Primary hydroxyl function give formaldehyde. For the fructose, again, the terminal C1 will be formaldehyde. The terminal CH2OH will be formaldehyde. So, 2 formaldehyde from C1 and C6. Now, here is ketone, and around the ketone we'll have 2 HiO4. So, CO will be CO2, carbon dioxide. And the secondary C3, C4, C5, secondary alcohol, will be formic acid. Predict the reactions products of methyl beta D glucopyranoside with periodic acid followed by hydrolysis. Or This is the methyl beta up D-glucopyranoside. Well, we have here OH, OH, OH. Adjacent to this OH, there is no OH. Okay? This is acetal, and this is stable. Well, now we have only two CC bond carrying OHs. Here is one, here is two. So we consumed only two equivalent HiO4. Between this carbon 3 and 4, we will have 3 and 4 one, and between 2 and 3 another one. So around C3 we have 2 HiO4, so it will be formic acid. What about C2? It's only one, so it will be an aldehyde. What about C4? Again, aldehyde functionality. Now, if we hydrolyze this molecule in acid media, we will not touch the stereochemistry configuration around C5, right? Okay, so we will hydrolyze here. C1 will be an aldehyde, acetal going back to aldehyde, and C2 is aldehyde already, so we get glyoxal. What about here? This one retain the configuration and there will be still R configuration. This is R, and here this is R, and of course here is R for C5. Okay, and we get glyceraldehyde, and because of the hydrolysis we get 1-methanol. Another reagent which can oxidize 1,2-diol to aldehydes or ketones is lead tetraacetate. Lead tetraacetate. Lead tetraacetate again form a cyclic intermediate 5-member ring which opens to 2 ketones or 2 carbonyls, and lead diacetate and lead diacetate. See you next lecture.